About corrosion and graphene's ability to give remarkable corrosion resistance. Why we are talking about corrosion? Because it is an extremely expensive affair. An economy like United States, it loses about $300 billion every year through corrosion. Any developed or developing economy loses about 4% of its GDP due to corrosion. And a small economy like Australia loses about $8 billion. So, and also corrosion is a thermodynamic reality, and it has been a vexing problem for a long time, right? Why I'm mentioning that is because it has been a long time problem. People have been doing variety of things like developing corrosion resistant alloys, stainless steels, aluminum alloys, or developing very good coatings, doing cathodic protection. So people have done almost everything they could to ameliorate or to retard corrosion. Again, why I'm mentioning that? Because of those facts, it is very challenging to be able to do something novel or disruptive in this domain. But if one could do something novel and disruptive, the rewards are huge. As I said, it is commercially very attractive to be able to mitigate the problem of corrosion. So with that background, what I'm going to show you today is that if you have a bare nickel and it is exposed to something like seawater for, say, a few hundred hours, you will have huge corrosion attacks on the surface of bare nickel. But if you had graphene coating on nickel, it does not corrode at all. It resists corrosion in a big way. As I said earlier, that it is very challenging. It is in fact scientifically prohibitive to be able to develop graphene on mild steel. And good news is that with some intelligent surface modification, we have been able to develop graphene on mild steel, which gives corrosion resistance once again in seawater type of situation for 1,000 hours or more. And the regions that I have, and I will talk about that in a sec, the regions that I have, there is no reason why this corrosion resistance should not be everlasting. At the moment, we don't have any coating which is everlasting. Under the sun, every coating is such that it eventually fades, like coating on your car or any other coating. But a coating on mild steel a coating of graphene on mild steel will be as good as being everlasting coating. And this work has been patented. It has been published recently, just last year, in a very good journal, and also it won an award in an award competition in Boston a few years ago. So seeing is believing, as you can see, that is graphene coated mild steel exposed to, again, seawater for over 1,000 hours, no corrosion at all. Whereas simple mild steel, 2 millimeter thick sample will be finished in few hundred hours. So that's what I'm going to show you. Another thing that I wanted to quickly share with you is that if you have graphene coated nickel and you expose it to harsh corrosion tests in different types of environment, like sulfuric acid, alkaline environment, neutral environment, irrespective of the environment, the corrosion resistance is same. Why I'm saying that is because the intercept of these two arms of this plot gives me corrosion resistance, this intercept, right? And that intercept value is same irrespective of what environment I'm doing this test in. Whereas if you have bare nickel, it corrodes at different rate depending on the aggressiveness of the environment. Like in sulfuric acid, it corrodes at much higher rate. You can see that corrosion rate is much higher. The higher the value, and it's a log plot by the way, higher the value of this intercept, greater is corrosion rate. So graphene coated nickel, it gives same degree of corrosion resistance irrespective of the type of environment, whereas the bare nickel corrodes at different rates depending on the aggressiveness of the environment. I have to be a bit fast. Recently, what is the meaning of this work? Is it applicable to real life or industrial situation? Indeed, it is. Bipolar plates of proton exchange membrane fuel cell. this component, bipolar plates experience very demanding environmental condition like sulfuric acid, highly aggressive, right? And when I have suitable alloy, like pure alloy of nickel copper with particular composition, it gives me very good corrosion resistance. Once again, this intercept gives me corrosion resistance, and you can see even if I'm trying to force it to corrode by by imposing anodic potential, it is not corroding much, whereas the pure nickel would have corroded at a very rapid rate. And then even other technique, electrochemical impedance spectroscopy, gives very reproducible results showing that it is very resistant to corrosion in this aggressive environment. Seeing is believing once again that the bare nickel would have been attacked, bare copper nickel copper alloy would have been attacked very easily, whereas graphene coated one does not corrode much at all. And this is a very attractive application. I will tell you why I'm saying that. The bipolar plates have this requirement of having good corrosion resistance, because even if you chose a highly corrosion resistant alloy like stainless steel or titanium alloy, it develops a corrosion product film, that is oxide or hydroxide. It develops on the surface, and that film is at the best semiconducting or non-conducting, whereas you would need this component to be conducting. So with period of time, because of formation of corrosion product, the conductivity is lost, and that's where there's huge problem. Graphene has this big advantage that it not only gives corrosion resistance, but also it is conducting, and I will talk about that in a sec. So with that background, let me get to the topic of what graphene actually is. We know what graphite is. Graphite is a layered structure as shown here, and one single layer of that is graphene. If you separate one single layer and characterize its physical properties, and if you did that before 2010, you will be winning Nobel Prize, because Nobel Prize was given exactly for that. So one single layer is graphene, as you can see. If you make a tube out of it, it becomes carbon nanotube. And if you make a ball out of it, it is carbon buckyball, which was given Nobel Prize as well. This single layer is a honeycomb type of 2D structure. It is two-dimensional. It is honeycomb type of structure, and each node here is sp2 hybridized carbon. And as I said, graphene has extraordinary properties. Its electrical conductivity, thermal conductivity, electron mobility, surface areas, all these are at least a couple of orders of magnitude superior to the nearest, like metal. Any metal having the best electrical conductivity, graphene has a couple of orders of magnitude superior electrical conductivity. And I will talk a bit more about the last 3 points, which are directly relevant for corrosion resistance. Graphene is 100 times stronger than the strongest steel, and generally when the material is strong, its toughness is poor. Like ceramic is very strong, but it is very brittle. Its toughness is not as good. Graphene defies that concept. It is strong, and at the same time it is tough, and it is very important because quite a lot of coatings, like ceramic coatings, because they are brittle, they give good corrosion resistance, but they are brittle. They can be chipped off very easily because they are brittle. So graphene is tough. Graphene is also inert. Even the highly aggressive hydrogen fluoride does not attack graphene. So the species that cause corrosion, like mild acids or chloride or oxygen or water, they don't have any chance of reacting with graphene. So graphene is inert, whereas common coatings like polymeric coatings, they can be attacked. They can degrade because of ultraviolet rays or caustic or other chemicals. Graphene does not undergo any chemically assisted degradation at all. And graphene is also impermeable. That little hole that you have in the middle of that hexagon, this little hole, is so tiny that even helium can't pass through. So water, oxygen, or chloride that causes corrosion will have no chance of passing through graphene. So what I showed you just now is that graphene is impermeable. Even smallest gas atoms like helium can't pass through. It is both tough and strong, and it is inert. Even hydrogen fluoride cannot attack graphene. There is no other material which has all these properties in one material. So the question is, can graphene be an ideal corrosion barrier coating? So that's the background of the talk. The first work on this topic was carried out in Rod Ruoff's group when he was in Texas. And what they did is that they took pure copper nickel alloy, and graphene coated copper nickel alloy and pure copper. And they exposed all the samples to air at 200 degrees Celsius. As you can see, copper and copper nickel alloy, they changed color because they oxidized, whereas graphene coated one didn't. That's why no change in color. They did another experiment. That was, they took a penny and they coated the upper half of the penny with graphene, and lower half was left uncoated. And they exposed the entire penny to a highly oxidizing hydrogen peroxide solution, and you can see upper half, which was coated with graphene, did not tarnish at all. It did not corrode at all, whereas lower half underwent corrosion. Ours was perhaps the first group which started to work systematically on graphene coatings for corrosion resistance. We had 4 or 5 PhD students, Nikita Chitre, which is under the combined program of IIT Bombay and Monash University, and other people were PhD students here, Abhishek, Tanjeed, Anisur, and another Abhishek. So they all completed their PhDs and they are working in industry, either in Australia, India, or United States. And other PhD students, some of them have become my colleague. Parama Banerjee was my PhD student. She is now senior lecturer at Monash University. Mainak Majumdar was junior colleague when we started to do the work. Last 5 names are very important. These were all undergraduate students. So we started this work actually as undergraduate final year project type of work. And graphene coated samples I got from Professor Ajian's lab in Rice University in USA. He's one of the world leaders in 2D materials. So the graphene coated copper samples that we got from Ajian's lab, first job for us was to make sure that indeed the coating that we had was of graphene. And how do you do that? By doing Raman spectroscopy. Raman spectroscopy, if it gives you these peaks, this peak is G peak, and this one is 2D peak. These 2 peaks are characteristic peaks for graphene. So once you have these 2 peaks, you can be sure that what you have got is graphene, whereas there's another peak D, which is for the defects in the graphene, and pure copper, which did not have graphene on top. Pure copper does not have these peaks, as you can see. So what we got from Ajian's lab is graphene coated copper, and we confirmed that, and it is only one atomic layer thick graphene. Why do I say that? Because as I increase the number of layers of graphene on top of metal, the G peak starts to become taller and taller compared to 2D peak. As you can see, that for 2 and more layers, G peak is taller compared to 2D peak. So what we got was single layer graphene because G peak is dwarfer, shorter compared to 2D peak. So with that, we started to work on corrosion experiments, and you can see once again the same plot that I showed you earlier. The intercept of this cathodic and anodic arms of this potential dynamic polarization plot gives me corrosion resistance. So graphene coated copper corroded at a rate which was 2 orders of magnitude smaller compared to the pure copper. I repeat, one single atomic layer thick graphene improving corrosion resistance of copper by 2 orders of magnitude. It's a log plot in sodium in a solution similar to seawater. And we also did electrochemical impedance spectroscopy, which confirmed what we saw in the potential dynamic polarization plot. And post corrosion microscopy proved that when you have pure copper, it formed cupric oxide. That's why dark color, whereas graphene coated copper did not undergo much corrosion. Around the same time, A few other people were also working on this project. So as I said, that we started to, graphene got Nobel Prize in 2010. We started to work on this in 2011, and we published a paper in 2012. And you can see that we were getting 2 orders of magnitude improvement in corrosion resistance, whereas one group from the United States were getting just less than an order of magnitude improvement, and another group was getting no improvement at all. So we were all working with graphene-coated copper and doing tests in corrosive environment. We were getting 2 orders, others were getting far less. And it's very good that we can claim, oh, we were getting the best results. But if there are some students here or young researchers here in the audience, I should share my view. It's all right to say that we are getting good results, but it's a good scientist will always try to know why others were not getting good results. Why we were getting 2 orders of magnitude, others were not getting as good. So far I say that there is variability in the corrosion resistance due to graphene in different studies. But around the same time, in 2013, just a year after our paper, there came a paper which says graphene, in fact, accelerates corrosion. Instead of giving corrosion resistance, it accelerates corrosion. And it was published in very reputable journal, as you can see. And as if one was not good enough, one was not sufficient, there was another paper published in the same journal. And see the title of the paper, Graphene as a Long-Term Metal Oxidation Barrier, Worse Than Nothing. What it's saying that if you don't have coating, it will be behaving better compared to having coating. So what was going wrong? What was wrong there? The thing that was wrong in their study was this, that they were not using good quality graphene. As a matter of fact, wherever the quality of graphene was good, corrosion resistance was still good. And in fact, they said that this lack of corrosion resistance due to graphene was happening because of disruptions in the coating. Wherever coating was discontinuous, corrosion was happening at high rate there, and which was not surprising at all. In our paper just a year before, we had said that you must be having continuous layer of graphene. If you don't have continuous layer at the locations of disruption, the corrosion is bound to be high simply because of this simple electrochemical fact that graphite is highly cathodic. If you attach graphite to any engineering material, it will force that material to corrode at higher rate because graphite will be acting cathodic, and the other metal that you're attaching it to will act anodic, and corrosion will be accelerated. That's what was exactly happening in their case. Fortunately, in our paper, we had clearly mentioned that your graphene coating has to be continuous. That discontinuity is not the only problem with graphene. Graphene also has this problem of developing wrinkles. But before that, Rod Ruoff's paper also showed that wherever you have inter-domain boundary, corrosion was happening at that location at higher rate. So I was talking about wrinkles. When you develop graphene on any metallic material by the process of chemical vapor deposition, it invariably develops wrinkles for very interesting reason. Graphene is one of the very few materials which has negative coefficient of thermal expansion. What does that mean? That when you cool it, graphene expands. So after CVD at the temperature of 900 or 1000 degrees Celsius, when you cool down, graphene expands and metal underneath contracts, and it adds to formation of more and more wrinkles. And wrinkles are bad for corrosion resistance because people have shown that wherever you have wrinkle, the corrosion can take place there because at the top of the wrinkle, the stresses can be so high that there will be rupture and corrosive can be passing through those wrinkles, and it will expedite corrosion at those locations. So you can see wrinkles are not good. So what I showed you so far is that graphene can have defects like boundaries, discontinuities, it can have wrinkles, it can have point defects. Like I told you that graphene has hexagonal structure, but instead you can have pentagonal structure, you can have heptagonal structure, and those are defects which can contribute to deterioration of corrosion. So what do? Either you find a way to form a continuous layer of graphene, and it is a painstaking job. Ajay's group would do it, and we got those samples and gave very good corrosion resistance. But in normal process, it is not easy to have discontinuity-free graphene. And if you have discontinuity, corrosion will be happening at those locations where you have bare area. So Abhishek Tiwari was my first PhD student to work on this topic. When he joined, he said that, why do you want to spoil my career? Because there are such beautiful papers published in beautiful journals that graphene is useless, and you want me to do PhD on that. And again, there may be some students in the audience. Well, this is what I told Abhishek, that look, let's do systematic work. Either we will prove whether they were right or wrong. In either way, it is a good scientific training. That is PhD is all about, not getting great results. That's not the purpose of PhD. The main purpose of PhD, main purpose is to do systematic work. So anyway, so we came up with very simple hypothesis. And what was that? That it is not possible to develop single layer graphene this with continuity. Why don't we develop multi-layer graphene? So this is what we did, that we have single layer, it has discontinuity. If we have multi-layer, it is most likely that this discontinuity will be masked by upper layers. That was a simple hypothesis we started to work with, and we developed graphene, and we could show that yes, you have wrinkles in the layer, but wrinkles of the lower layer is masked by upper layer, which may itself have wrinkles. So that was the hypothesis. Let me talk a bit about how do we develop graphene on metal by CVD process. What we do is that we take a furnace, we place the metal on which we want to develop graphene, and we heat it to high temperature, and then we pass hydrogen. Why do we pass hydrogen? Because most engineering metals will have a native layer of oxide on the surface, like copper will have cupric oxide. We want a pristine copper surface. So you pass hydrogen reacts with Cu2O or CuO, and it transforms into Cu plus H2O, and water is pumped out, and you have pristine copper surface. And then you pass hydrocarbon. It can be methane, it can be cyclohexane. In our case, it was cyclohexane, and we pass it in a very controlled fashion. That's why you have mass flow controller. So using the mass flow controller, we pass hydrocarbon at a very controlled rate, and hydrocarbon splits here because of this metal, and it splits into carbon and hydrogen. And if we maintain the right partial pressure, remember I said that we supply at very controlled rate. You have hydrogen and carbon formed because of splitting of hydrocarbon, and then you have graphene. If you maintained right partial pressure, you will have graphene. If you didn't maintain right partial pressure, you can have diamond, you can have carbon nanotube, you can have carbon soot. So other allotropes of carbon can form. For development of graphene, the partial pressure has to be quite controlled, and that is controlled by very controlled supply of hydrocarbon here. Why copper and nickel? Because both copper and nickel, chemical engineers will know, are very good catalysts for splitting hydrocarbon, and that's what we need. We want to split hydrocarbon to have nascent carbon, which can develop into graphene. And I said that copper and nickel are very good catalysts, so it is easier to develop graphene on copper and nickel, but the mechanism of development of graphene on copper and nickel our mechanisms are entirely different. And I will tell you what I mean by that. Copper has almost nil solubility of carbon. So whatever carbon is produced because of splitting hydrocarbon, if you have maintained right partial pressure, it will just reorganize itself as graphene on copper surface. Whereas nickel has huge solubility of carbon, 0.68% is much higher, huge. So the carbon that you produce, it will be diffusing into nickel, it will saturate it, and when you cool down, the solubility decreases with decreasing temperature, and carbon will be diffusing out, and it will form graphene. It will organize itself as graphene. And because of this difference in mechanism, it is difficult to form more than one or two layers on copper, but you can form multi-layer graphene on nickel. And if you remember, our interest was to develop multi-layer graphene. So here onwards, we started to work more on nickel because it is nickel which has ability to develop multi-layer graphene. We developed copper with multi-layer graphene, or 2, 3 layers of graphene, and that copper, that graphene-coated copper gave corrosion resistance not improvement by not more than 10 times or so. So we developed our own graphene as opposed to the graphene, good quality graphene coated copper we got from Ajay's lab. And you can see that improvement is just by less than 10 times. But, and it's multi-layer graphene because G peak is taller compared to 2D peak, but it has lots of defects. But the most important thing is that first time we could show that whatever improvement in corrosion resistance happened because of this multi-layer graphene, that sustained for 400 hours. That was the entire duration of test in sodium chloride solutions. For the first time, we could show that if you address the problem of discontinuities or defects in graphene, you can have long-term corrosion resistance. My other student, Anisur, he also worked and he could show that that improvement can last for more than 1,000 hours and can continue. We did microscopy to prove that. But as I said, that our interest shifted mainly to nickel because we had interest in developing multi-layer graphene, and it is nickel which can develop multi-layer graphene far more easily. We started to work on tailoring the CVD parameters further so that we can develop graphene of good quality, graphene with less wrinkles. And in one particular condition where we did rapid cooling after CVD at 1,000 degrees Celsius, but in the environment without hydrogen, it produced graphene with less wrinkles, and Raman spectroscopy proved the quality of graphene. So this is the particular condition in which we could develop very good quality graphene, and that graphene gave very long-term corrosion resistance. As you can see, it is statistically proven data that graphene that was developed with rapid cooling and without hydrogen, it gave very good corrosion resistance that lasted for over 1,000 hours. That was the entire test duration. Whereas if your graphene development conditions, CVD parameters were not correct, if you are doing rapid cooling with hydrogen and graphene quality was not good, then improvement was not good. So here you have, as I said, statistically proven data for graphene giving very good corrosion resistance to nickel in sodium chloride solution, highly corrosive seawater type of solution for 1,000 hours. And there is no single reason against the statement that this corrosion resistance should last forever, because graphene will not deteriorate with time. As I showed, that it doesn't react with any chemical. It is tough, and also it is impermeable, so it will last forever. One can very confidently say that this will last forever. And again, you have seen this earlier, that graphene coated nickel graphene produced in this condition, rapid cooling without hydrogen, gave very good corrosion resistance that will, and we published this again in a very good journal. And I talked to you about bipolar plate and use of graphene coating. We first worked on copper, that was earlier, and we published in a journal, again good quality journal. But later on, we started to work on pure nickel, and that gave very good corrosion resistance, much better than mono, which is an alloy of nickel or copper. So graphene coated nickel, pure nickel, gave very good corrosion resistance. And as I said, that it is very useful because it not only gives corrosion resistance, but graphene is also conducting, which is one of the characteristics that is required for bipolar plate application. Corrosion data, as you can see, more than 700 hours in highly corrosive sulfuric acid environment. And again, this work was published in Carbon. And post-corrosion characterization, you can see it is before corrosion test. After corrosion test, you have only a few spots here and there. Otherwise, it is corrosion-free. Whereas bare nickel in this condition will be finished. A 2 millimeter thick sample will be finished in no time. So what I showed you so far is that we were successful in developing graphene on copper-nickel alloy, but there were small samples. Can we develop it on large area? Can we play with the CVD parameters further to be able to develop graphene on large area? And can we develop graphene on steels? So I will take you through the rest of the journey. It will take another 5-7 minutes, and I will finish. That this is the CVD chamber, And what we had been doing before this is that we were keeping the sample flat. So our new student who had just now completed his PhD, Abhishek Arya, he came up with the idea that if we keep it tilted, then on the basis of the fluid dynamics, there will be much better distribution of the precursors over the surface, much more uniform distribution of the precursor. So we developed graphene both under the condition of 5-degree tilting and 45-degree tilting. And you can see that 5-degree tilting had graphene with lots of defects. You can see very clearly the SEM images show you. Whereas 45-degree tilted has very little discontinuity. The graphene quality was very good. This paper is about to go, that aspect is about to go for publication to another journal. And we did Raman spectroscopy and Raman imaging of this 2D peak very clearly shows that 45-degree tilted sample had much more uniform graphene. You can see that all the spectra taken from different locations are uniform or similar, whereas 5-degree tilted sample has spectra where at some locations you have very good graphene, multi-layer graphene, some locations don't have very good quality graphene, and you will realize this in a sec. And when we did corrosion tests, you can see that 45-degree tilted sample gave very good corrosion resistance. Post-corrosion macroscopy also showed, you can see 45-degree tilted as graphene, good quality graphene still intact, whereas 5-degree tilted one had disruptions in the coating, as you can see, disruptions in the coating, and the 45-degree tilted gave very good corrosion resistance in sulfuric acid for a long time, over 1,000 hours or so. We take a bit of pride in this particular work because this was the first time this scanning photoelectron macroscopy was used in corrosion research. It was done with the help of Trieste synchrotron. What I'm going to show you is that when we had 5-degree tilted samples, there were disruptions in the coating. Because of disruption, the nickel substrate was exposed, and when you expose that to sulfuric acid, it forms sulfide. That's why you have signal for sulfur, you have signal for nickel because of disruption in the coating, and the carbon itself, the graphene, was not uniform over the surface. Then you had disrupted area. So disruption here exposed nickel, which reacted with sulfur, and we could understand it further. Whereas 45-degree tilted sample, you can see no nickel signal because we had very good graphene coating on the top. Carbon is very uniformly distributed on the surface, and no sulfur because we didn't have any bare area. So that was about nickel. Coming to the last 5 minutes of my talk, so we showed you our ability to develop graphene on copper nickel alloy, and also improving the CVD parameter to get even much better graphene, which gives superior corrosion resistance. Can we develop graphene on mild steel? Answer is, it is a huge challenge. What is the challenge? Challenge comes because if there are some metallurgists in the crowd or in the gathering, they will understand iron or steel at high temperature like 900 to 1000 degrees Celsius has face-centered cubic structure. Why 1000 to 900 degrees Celsius? Because that's the temperature for CVD, chemical vapor deposition. But iron and steel is body-centered cubic at room temperature. Why I'm talking about crystallographic structure is for the simple reason that face-centered cubic structure has 100 times greater carbon solubility. So at high temperature, lots of carbon will be dissolving in iron lattice, in the face-centered cubic lattice. Fine, dissolves, that's good. When we cool down, there will be a phase transformation from FCC to BCC. And remember, I said BCC has 100 times less carbon solubility. So all of a sudden, a lot of carbon will be rejected from steel or iron, and carbon supply to the surface will be so much, it will be so excessive that developing graphene will not be possible. So this is a prohibitive scientific challenge because of which one cannot develop graphene on mild steel by CVD. I'm talking about pristine graphene. Okay, that's the main trouble. So it is a non-trivial task. But if we manage to develop graphene on mild steel, it is a hugely attractive, commercially attractive proposition. You don't need to use stainless steel. Graphene put in mild steel will work much superior to stainless steel. You don't need to maintain coating because graphene does not degrade with time. Good news is that we have been able to develop graphene on mild steel, and that graphene coated mild steel gave corrosion resistance for 1,000 hours, and you can see it is statistically proven data that there is no reason why this coating will degrade. Nothing will happen to graphene coating. It does not react. It does not allow penetration by corrosives. And we had 2 orders of magnitude. Again, you can see that the graphene coated mild steel, and after immersion for 1,000 hours, no change. Whereas mild steel as such would be corroding very fast. And as I said, that this work was again published last year. So, how did we achieve this? We said in earlier slide, it is a non-trivial research task. How did we achieve this? We undertook some obvious surface modification before trying to develop graphene. That did not work, and I will tell you what that obvious surface modification is. We had success in developing developing graphene on nickel. Why don't we develop a very thin layer of nickel on top of mild steel, and then you try to develop graphene on nickel? It does not work. It doesn't work for a very simple reason. Those, again, who know metallurgy will know that iron too has very high solubility of carbon. So whatever carbon diffuses into nickel, it leaks into mild steel. So you have mild steel substrate. On top of that, you have nickel coating. Yes, you will have splitting of hydrocarbon. You will have carbon diffusing into nickel, but that carbon will leak across the interface into the mild steel substrate. So that's where was the problem. That's why we could not develop graphene. Raman spectroscopy says that no graphene and no improvement. So where is the problem? Problem is because carbon that will be dissolving into the nickel layer will diffuse into mild steel. Why don't we put a layer in between which will stop carbon from diffusing to mild steel? And what is that? It is copper. You remember earlier I said that copper has nil, insignificant solubility of carbon. So carbon will be retained in the nickel layer because this copper layer will not allow carbon to diffuse to mild steel. In the absence of copper, whatever carbon was there in the nickel, it will diffuse into mild steel because both have high solubility of carbon, but copper will stop it. So we developed a thick layer of copper, very thick layer of nickel, and again we could not develop graphene or good quality graphene simply because lots of carbon diffused and carbon content of nickel layer was so high that it defeated the whole purpose. And also thin layer did not work. We had thin layer of copper. I don't have time to go into details, but I will come to the real solution. So what we did, we undertook very good diffusion calculations that during the time temperature window of CVD, what is the length to which iron and carbon and copper can diffuse. We don't want iron from the matrix to diffuse to the surface and jeopardize graphene development. We don't want even copper to come to the surface because copper will also not allow multi-layer graphene development. So we optimize the thickness of the layer, taking into account the CVD time and temperature, and we came up with the idea of about 10 to 12 micron to be safe. We deposited 15 micron thick copper layer, and then we deposited nickel on top of that, like as I showed you here, that 15 micron of this, and then another 15 micron or 13, 15 micron of nickel. And then we subjected it to CVD, and we developed beautiful graphene layer. Very good layer, not much defect. G peak is much taller compared to 2D peak, so it is multi-layer graphene, and that multi-layer graphene gave very good corrosion resistance, as you can see here, and that corrosion resistance, I'm showing this plot many times, lasted for over 1,000 hours. If you had just nickel, copper nickel layer, you can say that improvement happened because of just nickel layer. Nickel also gives corrosion resistance. If you had just copper and nickel layer without graphene, it corrodes, and corrosion resistance is not as good. But if you have graphene on top of that, it gives very good corrosion resistance, more than 2 orders of magnitude improvement, and statistically proven data. it gives perhaps everlasting. There's no reason why this corrosion resistance should not be everlasting. So I hope what I showed you today is disruptive in terms of developing a coating which gives everlasting corrosion resistance. In that sense, it is disruptive. It is novel because if we tried simple technique, simple approach of just developing nickel and then graphene, it will not work. We had to undertake the development of the dual layer of copper and nickel as prior surface modification before undertaking CVD for graphene development, and that's how we were successful. Thank you very much. How do I get back to the audience? I hope the audience could hear the talk.